what's up, YouTube? I think that we should be live any second now. Yes, we are live. What's up? How's it going, YouTube? If you're new, my name is John. I am a former math major turned software engineer, and now I'm trying to rebuild my passion and love for math by running a practice stream here on the internet. So I just show up and do my regular math practice, and it's nice to just hang out with you all while I do that. Uh, I apologize. You might notice that my voice is still pretty messed up. I've been away from streaming for like 2 weeks, and I'm still getting over this flu. It's been really rough. But I think that we're good enough to go today. I'm finally ready to get back to streaming. So, today we are resuming our studying of linear algebra. We are now in chapter 3. And I might give my voice a rest and just solve some of these problems quietly if that works for y'all. So, I hope you enjoy. Let's have background music. Let's use my background music. So, this is my winter recital from my classical guitar practice channel. Hey, Ramon, what's up, man? The classical background music I understand. The rest I can figure nothing. Yeah. It's linear algebra, dude. It's linear algebra. It's not so bad. I could teach you. Good to see you, man. Thanks for stopping by. Man, my voice is still fucked up. I don't think that this is going to be a linear transformation. This addition is weird because of the +1. Like, adding a constant, it doesn't seem like I don't think that this is going to be a linear transformation. Or a vector space. So, properties of a vector space. We need a 0, additive 0. So, we need some element 0 such that 0 plus x equals x. Yeah. You've seen some of this? Cool. So, with this, I don't think that there would be anything. We want something such that 0 plus AB equals AB, right? And this is fancy addition. Well, with our fancy addition, whatever this is, I'm going to call this Z1 and Z2 to remind myself that this vector should be, it should be the 0 vector. Or like, these should be two elements such that we get this property. Plus AB equals, we want this to be true. But this fancy addition, that looks a little too much like a swastika. We have x plus a plus 1 and y plus b. We have z1 plus a plus 1 z2 comma z2 plus b to equal ab. Then z1 plus a plus 1 has to equal a, so then z1 is negative 1. Okay, I mean, maybe that could work. And z2 plus b equals b. z2 equals 0. So, negative 1 comma 0 plus any vector xy is going to be xy. I was going to make that comment, but you did. What do you mean? Which comment? Which comment was that, Ramon? Oh, that I've been sick for too long? Or something else? Man, my voice is all messed up. Oh, yeah. Yeah, that was a little messed up. I was like, I don't think that's not what I'm trying to draw here. In the book, it's like, that still looks a little gnarly. Yeah, I don't like the symbol that they're using. I don't like it. I'm just gonna, what I like instead is like a plus with a circle. Let's do plus with a circle around it. This is a special plus. Does look a little funny. Special plus. There we go. That's better. Special plus. I mean, this symbol does mean something different called the direct product, but we're just going to ignore that. That's okay. I like plus with the circle around it. Okay, so negative 1 comma 0 added to xy will be xy. So there is a 0, an additive 0. We need negative vectors. Additive inverses. So we need some kind of I'm going to give this the name n1, n2 for like negative. And the 0 vector we found was -1, 0. Right? For the purpose of this situation is a plus with a circle. What is the plus with the circle? Is that what you're asking? The plus with the circle is here. It's a special addition that's defined differently than usual. So xy plus ab, normally we add two vectors and this would just be x plus a, y plus b. But in this case we're also adding 1 as well, so it's like a unique new addition. Okay, so here I meant to write all that in blue, but oh well. It's fine, who cares? Let's switch to blue now. xy plus n1, n2 equals -1. Our special addition would have x plus n1 plus 1 and y plus n2 equal -1, 0. So the plus sign now here is like regular addition. But this is like a unique, strange operation. Like it's an indicated different operation of addition. And we're trying to decide if this thing is a vector space. So here, well, we need to solve these equations. X plus n1 plus 1 equals -1, and y plus n2 equals 0. Well, yeah, this works out. N1 is -x1, -x minus 2. And 2 is -y. So an additive negative, or like the subtraction of a vector is that. Like here we can see x, y, fancy addition with -x minus 2 and -y. This equals x plus -x minus 2 comma y minus y. Oh wait, and then a plus 1. And then this is -1, 0. Yeah, that explains the -1, 0 thing. Like, what's up with -1, 0? Yeah, this is now the 0 vector in this problem. And I found that -1, 0 that this is 0, the 0 vector, by following this property and seeing how we can solve to see what vector would satisfy 0 plus x equals 0. Okay. So, well, we found an additive 0. We found additive inverses. Let's see. I think we need commutativity. I think we need this. Well, I think that this is going to work out. A1 fancy add B1, B2 is, with the fancy addition, we have A1 plus B1 plus 1, and in the second component, just A2 plus B2. And, well, this is the same as commutative is, or addition is commutative in the regular addition in the first component, and same in the second component. And this is, by definition, B1, B2, fancy addition with A1, A2. So, yes, this property holds as well. We have commutativity of addition. There's another one I'm missing. Maybe it's the associative property, I think. Associative property of addition. So, we need to check that. This is going to work out. I switched to yellow. Oh well, that's fine. Starting to feel like this will work out. Yeah, I think that this operation will create a vector space. So this is now A1 plus B1. I'll do it in 2 steps so that we can really see it explicitly. And now we can, this is kind of taking 2 little steps here, but we can regroup this. Oh, yeah. So there's a little bit of regrouping here. But those first components are equal. The Jonathan continues. Yeah, the Jonathan. I like that. Yeah. The marathon, the Jonathan. Yeah. Against my better judgment, my voice is still messed up, isn't it? Good to see you, Skittles. What's up, man? We're doing Fancy Edition. And, to determine if this is a vector space created by this weird Fancy Edition. Yeah. So, this is A1 plus B2 plus... Oh, wait, no. Oops. Should be B1. Yeah, that was a typo. That was a typo. And then here we have... Am I doing this right? A1 plus B1 plus 1. A2 plus B2. C1 plus 1? Is that what I meant to say? This looks a little broken. Something looks broken. Something looks broken. The Jonathan. It's just been sitting right there this whole time. Oh. Oh, yeah. This would just be with C1, C2. That's correct. This is fine. Because this one evaporates or something. It gets... It came from this fancy edition adds that one. Ugh. Okay. Yeah. This is fine. And now this is the same as A1, B1, Fancy Edition with wait. This is A1, A2, Fancy Edition with B1, B2, Fancy Edition with C1, C2. So then, therefore, we have the property of... We've proven associativity of addition. A plus B plus C equals A plus B plus C. So this one worked. I think Tzok came up with the name before you did. Pretty weird sync, actually. The name Jonathan. That's cool. Yeah. Or something else. Wait, like is Tzok thinking of doing a marathon stream, or what are you talking about? Okay, so we got existence of a zero, of an additive zero, existence of additive inverses, commutativity of addition, and associativity of addition. I think that those are all of the additive properties that we need to check. Next, we have the scalar multiplication properties. So, we need a vector 1, or a scalar 1, such that 1x equals x. Existence of multiplicative identity. So we need I think he randomly said it before you came up with the marathon idea. I'll have to go back and find it. That's cool, really. That's hilarious. Yeah. No, that is definitely a coincidence, for sure. The John-a-thon. Like, if I've been streaming a lot, has he called it a Jonathan lately? Or at some point? Yeah, that's funny. Okay, so we need some vector or some scalar where we're defining Rx like this. So we have R times xy equals Rx plus R minus 1 and Ry. This is interesting. So it's like a fancy multiplication. So we want to find some idea of a 1 multiplied by a vector xy, which is going to be r1x plus r1 minus 1 r1y, and this should be equal to xy, because we want multiplication by a 1 times x, we want to be x. Like, it's a multiplicative identity. We always want 1 times x to equal x, even when we go to weird, different number systems. So here, we need to solve these equations. So we have r1x plus r1 minus 1 equals x. How can we solve this? Well, I suppose we could factor out r1 and add 1 to both sides. right? And then we can divide by x plus 1, but that requires x not equal to negative 1. Or really we just need to say that R1 is 1, like in the regular numbers. Yeah, R1 is just the usual multiplication by 1, addition by 1. Yeah. The usual 1 in the usual real numbers. It works. Okay, cool. And I think it will work the same here. Of course it does. R1y equals y. We can solve that as R1 equals 1 as well. So, yeah, we do have a multiplicative identity. We need... I don't know what else. Man, gotta go. Maybe you'll be here later. Take care, Ramon. I don't know how long I'm going to do a math stream today. I might just do this one problem, if I'm totally honest. But I'll probably be switching over to the guitar stream. So check the guitar channel if I'm not here. Thanks for stopping by, man. Good to see you. Okay. So that, we need a multiplicative identity. We have that. We need a multiplicative 0. Now, we need to be careful here, because here this is the 0 vector, and here is the 0 scalar. So, defined by these rules, I'm going to give this the name R0. And we're multiplying by some two-valued vector. And the 0 vector in this that we found earlier is -1, 0. Right? So then the left-hand side, we have our weird multiplication. R0 x1 plus R0 minus 1, comma R0 x2 equal -1, 0. Then we have two equations. We have R0 times x1 plus 1 minus 1 equals -1. We can solve that. R0 equals 0, the usual real value 0. And yeah, it works in the second component as well. R0 x2 equals 0, R0 equals 0. Cool. So we have a we have the 0 scalar. I think we might need to explicitly say that we have a... Like, really we need to say that the scalars form a field, which means that for any x, there exists an inverse, a multiplicative inverse. And I think we inherit the field structure of R for A inverse equals 1. A inverse is 1 divided by A. That is, we also have properties like we have to have commutativity of multiplication, commutativity of addition. We inherit all the standard field structure of the real numbers. The properties that we really need to check, yeah. Okay, yeah, the ones that we really need to check are the way that we combine the addition and scalar multiplication. So we need R times A plus B to equal RA plus RB. And remember that this is fancy addition. Fancy addition. So let's see. The left-hand side is R times A1 plus B1 plus 1, A2 plus B2, which is combining with our fancy multiplication, R times A1 plus B1 plus 1 plus R minus 1? Is that right? Plus R minus 1. Yeah. And then R times A2 plus B2. Then why do I feel like I'm missing a minus 1? RA1 plus RA2 plus R minus 1. Ah. Cool. We're getting somewhere here. We're getting somewhere. Look at how neat that is. So, yeah, I can't believe it, but this thing is forming a vector space. I'm pretty sure. Pretty sure. Now, this is written in the way that's RA1 plus R minus 1 RA2. Fancy addition with RA2 plus R minus 1 RA2 RA2 plus RB2 Wait, what am I doing? No. Wait a minute. Slow down, John. Slow down. Yeah, I made a mistake right here. This I meant to write B1. Yes. Found it. Yeah, I knew something was off. Okay. RB1 plus R minus 1, comma, RB2. Yeah. And now by definition of our fancy multiplication, this is R times A1, A2. Fancy addition with R times B1, B2. So, voila. We do have fantastic. We do have distributivity of scalar multiples. We have another distributive property that we need to check. So now I'm going to use R1 and R2. Let's see. We need to check that A plus B times X equals AX plus BX. So if we have two scalars that are added, that we can distribute the vector across them. So let's take, I like those letters. Let's use those. A plus B scalar multiple with x1, x2 equals, well, our letter R is A plus B times the first component plus A plus B and subtract 1, and then A plus B times the second component. Then here we have AX1 plus A bx1 plus b. There we go. Yep, this is going to work. And now this is ax1 plus a minus 1, comma, ax2. Fancy addition with bx1 plus b minus 1, comma, bx2. Yeah. And this is, by definition, a x1, x2. Fancy addition with b x1, x2. So we got distributivity of two scalars and one vector, whereas the other one was distributivity of one vector and two, or one scalar and two vectors. So hell yeah. What else do we need to check? I think we already found the existence of a 1. We found the existence of... Doesn't seem to require a 0 scalar, but... I guess we do have this one as well. RSV equals RSV. So I've been using A's and B's, so let's continue with that. ABX equals, this is how I've been writing these, but tomato, tomato, whatever, however you want to write it. So let's start A times BX. This is A times B. We have two components. This is A times, doing our fancy multiplication, it's bx1 plus b minus 1 and bx2. Now we do another fancy multiplication. Let's see. We have a minus a and plus a, so this is minus 1, yeah, and we're pretty much done. So, what does the book call that property? The book calls that property associativity, probably, or yeah, an associative law. It is associative. Okay, cool. That makes sense. All right. I'm sick, so I think that's it for today. We're just going to work that one problem. It's almost been an hour, so hell yeah. Thank you for watching, if anybody is still around. I'm going to go over to my other channel and practice some more classical guitar. So see you there. Thanks for watching. Bye. Bye. Good Lord, I need some more tea.